Now that we've seen the different settings that can be used for setting up the simulation mesh using the Mesh Settings tab of the Solver region and Mesh Override regions, we'll go over some tips for setting up the mesh. Using a combination of the Auto Non-Uniform Mesh type with Mesh Override regions is recommended, since it allows you to control the mesh based on a target number of mesh points per wavelength, and also allows you to specify a finer mesh where needed to resolve fine geometric features or regions that are sensitive to meshing, such as interfaces between metal and dielectric materials. When using the Auto Non-Uniform Mesh, the mesh accuracy setting of 2, which corresponds to 10 mesh points per wavelength, is considered reasonable for the FDTD method, and mesh accuracy of 4 or 5, which corresponds to 18 or 22 mesh points per wavelength, is considered high accuracy. It's worth running the simulation at mesh accuracy 1 or 2 for initial simulations in order to be able to run simulations more quickly before refining the mesh for higher accuracy results, since the simulation memory scales as 1 over dx to the power of 3, and the simulation time scales as 1 over dx to the power of 4. For mesh refinement, as mentioned earlier, Conformal Variant 0 applies conformal meshing to all materials except metals, and Conformal Variant 1 applies conformal meshing to all materials, but it can sometimes lead to numerical artifacts if the mesh is too coarse. So a simple rule of thumb is to always use the default Conformal Variant 0 method, and only use Conformal Variant 1 when convergence testing of the mesh step size will be performed for getting high accuracy results. Comparing the results obtained using Conformal Variant 1 and Conformal Variant 0 is also recommended to make sure there are no major discrepancies between the results when using Conformal Variant 1. After setting up the simulation mesh, the mesh that is generated can be checked by using the View Simulation Mesh button to show the mesh in the CAD viewports. And you can also use the refractive index monitor to view the mesh structure. The mesh that is generated will try to meet several constraints, including placing a mesh line at the position of 2D objects, placing mesh lines at the edges of mesh override regions, grading the mesh between fine and coarse mesh regions, and meeting minimum mesh step size constraint. Sometimes it's not possible to meet multiple constraints at the same time, so it can be important to check the mesh that's generated and make sure that it's reasonable and that all of the structures are adequately resolved. When simulating periodic structures, it's best to use a mesh with an integer number of mesh cells per period in the direction of periodicity, in order to make sure that each period is meshed the same way. This will ensure that the simulated periodicity of the structure will have the same periodicity as the physical structure. And this can be important for devices such as cavities or resonators, where the quality factor and resonance wavelength of the cavity is sensitive to the periodicity of the structure.